Okay, we're live. So I've created a study guide. It's in the Canvas shell. Um, and so let's just go over everything. All right. So there'll be 5 questions, and this is the order of the question, right? And it's kind of the algorithm that I'll use for generating the questions. All right. And so even though this is the study guide, it's probably best to put some things here. All right. So these questions, although some would be easy to automatically grade, for the most part, drawing a schematic and coming up with a unique design would take an enormous engineering effort to come up with some code that would automatically grade your exams. So really, my open math will deliver the exam only, right? So the if you have an accommodation, the accommodation time is in the upload part of the exam, not in the delivery part. Okay. And so just as a reminder, right, you open up your exam, you want to save a copy right away, right? And it's print PDF. I'll give some reminders. I know that we can get into an alternative reality when we're in an exam. Really, just do the best you can with doing that. Okay. But other than that, it's the same format. All right. So question 1, you're going to draw the schematic of implementing a DF2 base filter, which if you're trying to Google more information, everybody else calls it state space, except this textbook. Okay. So things that I thought were good to remember, and it's almost my grading guide, right? The highest order of the denominator is the number of inverting integrators you need, right? The A summer, which is, in general, the first summer you draw, you're implementing negative feedback. And what that means is that every item needs to be negative when you add it. So if you have an odd number of inverting stages, right, it's already inverting. So you bring it in on the positive side. And if you have an even number of stages, right, you need to invert it. So you bring it in on the negative side, right? And then as you go down the schematic, yeah, the output of the A summer is the highest order of S in the transfer function. And then the next integrator is one less order. And that happens all the way until you have S to the 0 power, right? Now, the B summer is used to sum the parallel output of the orders of S, okay? and I should say in the numerator. All right. And I'm going to go into, I'm just going over the sheet now. I'll go and, you know, find some examples of what that means. But, you know, if there's only one output, meaning there's only one term in the numerator, and if it's not inverting, well, then you don't really need a summer to come after it. All right. And if you only had one output and you needed, all you needed to do was an invert it, well, you don't really need a whole summer. You just need an inverting op amp gain stage. All right. Now, the B summer is implementing regular addition. There's no negative feedback. It's not positive feedback. Some call it feed forward, but it's just regular addition. So that means the odd stages, right, they go on the negative side. So because a negative times a negative is a positive, and the even stages go on the positive side, right? Now, the other thing you need to be able to do is draw about, you need to be able to balance an advanced summer, right? You don't have to come up with the values, but you need to be able to kind of determine, you know, whether where the dummy goes, where the dummy resistor. And then, yeah, you kind of need to know what an inverting integrator is right off the top of your head. All right. So, but yeah, you could have a high, a low, a band, a notch, second order, fourth order. There's band and notch can really only be, at least for Butterworth filters, can really only be even. All right. Low and high can have an odd number of stages, but what I found is that it's some odd things can happen when I have an odd stage. So really, you can be expecting, you know, like a second, fourth, or even a sixth, right? And you'll get the transfer function, and then you just implement it. Now then question 2, it's on gain bandwidth. And these questions, it's really, the open loop gain is a function of frequency, right? Another way to write that, right, is it's just this, right? Open loop gain is a function of frequency, but normally, right, I'm giving it to you in terms of there's an H there's a transfer function of the op amp. All right. So that's the thing we normally use, right? But some things to know, right, to make sure that you know, is that the open loop gain, the AVL term that you would see on a data sheet, right? So even though open loop gain is a function of S, the reason why I use H of S is that this term is the open loop DC. It's like it's 1 point, or when S equals 0 or frequency equals 0, right? That's why rather than use this term, I use this, right? The gain bandwidth, right? Even though, and that's the kind of thing we're talking about, right? It's the DC spot, and it's the spot where the open loop gain equals 1 or 0 dB. Okay. And I'm going to fix these. Andrew, yeah, I got a lot of notes on what the B summer is. Okay. So I'm going to get back to you on that, I think. So do you have to calculate RNC values? No. That would be an exam with one question. Design and implement an LT spice, a DF2 filter with a particular transfer function. Okay. So, Andrew, and I don't mean to call you out. It's just, I'm going over the sheet, and then like the details and questions I'll take later. I must have programmed this wrong. So anyway, using control theory, you find, so one of the there's several questions. Using control theory, right? That means you have an op amp transfer function. Mathematically find the frequency range where that will work, right? And what would you get? Low pass, high pass, non-inverting gains, things like that, right? The other kind of question is you got to do the same thing, but do it graphically. And those kinds of questions, really, it would be an inverting integrator or an inverting gain stage. Now you can do those mathematically, and I do have them worked out, buried in my, terabyte of information that I throw at you. But really, graphically, those are the two easiest ways to, graphically, those are the things that are better to do that way because it's easier, right? Then another kind of question is you get an op amp data sheet, and you need to determine the gain bandwidth and the open loop gain at DC, right? And then the final thing is recognize, from a list of symptoms, when a circuit is not behaving ideally. All right. Now the thing is, right, as we get into this, right, the homework, there's homework that's basically all of that, right? Now there might be assignments that I had you do to lead you up to question 1, but really any homework that says here's a DF2 filter or transfer function implemented in DF2, that would be a valid question to study. Same with gain bandwidth, right? You'll see that a lot of them are do it graphically or do it mathematically. And then there's also another one, I thought I wrote it in here. There's another kind of question. Determine if a feedback configuration is over critically or under damped, right? Now in the homework, I might have had one transfer function and I made you do it like 4 different ways. On an exam, it'll only be just the one, okay? And I'll fix this later. But it's really open loop gain divided by S, open loop gain divided by a real pole, and open loop gain divided by 2 real poles. All right, that's all that is. All right, so the mass spring damper, spring mass damper. You're going to get a picture and you need to draw the RLC schematic. And that means labeling it. What's V out? What's the VX, VY, right? And then derive the transfer functions in terms of S, R, L, and C. But you won't have to, you're not going to get a problem where I'm giving you the damping coefficient, the mass, and the spring coefficient, and then you have to convert that to something, and then convert that to R, L, and C, and then determine if it's over, under, or critically damped. All right. You just come up with the picture, right? And you have to label the picture properly. And then based on that picture, you have to, well, I should say you've got to get the transfer function correct. And then what the third part would be, what happens to that transfer function if the damper or the spring completely breaks away or freezes into a steel rod, which means there's no springiness to it, and it passes movement 100%. Okay. Then the fourth question is control, right? And you get a transfer function, and you get it, and is it in or out of control? And I think I can guarantee that every transfer function on the exam is out of control, right? But you have to explain why, right? You can't just say Descartes' rule, or it's, hey, there's a real pole at 0. That means it's an integrator. The step response will become a ramp. Output doesn't go to a constant value, right? That's the whole explanation. You could have a real pole at plus or minus real poles, right? Because that's a pair at plus or minus j omega. And the step response of that is an oscillator. Output does not go to a constant value. And believe me, you better be, just as a gentle hint, make sure you're using your own words on this. This is kind of like a cheat sheet, if you will, right? You could have a real pole or more than one real pole greater than 0, right? The step response becomes an exponentially increasing signal and does not settle. Now, here's the thing. You can have complex poles where the real part is greater than 0, right? And it doesn't really matter if it's oscillating to infinity, right? It just exponentially increases, right? So that means you need to be able to calculate poles. I've revamped the thing where everything is second order on the exam, okay? If you want to learn about higher order things, then EE 132 is the course for you. All right. And calculating that is just the, right? It's just a quadratic equation. Okay. And then you need to design a feedback network to take a second order system that's out of control and make it makes it into a system that is in control, right? And then once you've done that, you have to set some constraints on K, K1, K2, what have you, to ensure that it is in control, right? Because just because you propose a feedback network, there's values of K have to be at least a certain value to make sure that the system is in control. All right. Now for the FFT, and I put that last because I feel that these topics kind of really flow, right? But if I don't start the FFT when I do, then you won't understand what's going on in lab, and you need that to do the final project. That's why things are in the order they are. All right, so what are the possible questions? Determine the Fourier expansion coefficients of a sign graphically, right? And I'll even, A0 average of the signal, right? ANs, right? 2 times average of the signal times cosine omega naught nt. B naughts. Okay. And that omega naught is like 2 pi f, right? Or 2 pi divided by t. And n is 1, 2, 3, 4, 5, and so on. Right? That's real. That's the definition of the Fourier expansion, right? Just said in words instead of mathematical terms, right? Then another kind of question I like is the matching game, right? And here are some possible things that need to be matched, right? You have a square wave with a certain duty cycle, right? And what are you matching? All right, so you have a time domain to FFT spectrum, right? So you have a square wave with 50%, 25% duty cycle, right? What is it, right? You could have two sine waves that you're adding together. You could have two sine waves that you're multiplying together. You could have sine omega 1 squared, which is really like if these omegas were the same, sine to the omega cubed. And, there's various, not quite an infinite variety, but really, you don't actually have to find the Fourier expansion of all of those signals. You can just kind of tell, oh, this signal has a DC offset. This one doesn't. This one has the right harmonic, the right fundamental frequency. This one doesn't. And you can almost answer all of these with just the first two harmonics, right? So, that's pretty much the exam. Now, yeah, I just don't have an exam generator automatic question thing like I did for exam one. In retrospect, that was a lot of engineering effort for exam one that I couldn't possibly do for the other ones. But let's just go over more information. So here's the review. Sometimes I have other midterms with answers, sometimes without, sometimes with, right? Exam, and here I have, extra exam type problems, okay? And then on the midterm, I have various midterms with solutions, right? And so you can use those to test yourself, right? Just be aware that when I do a solution, I might be giving more information than what I would expect the student to be able to do. Or I'm like, now that you've taken the midterm and you can understand things at a higher level, I'm going to start teaching you newer things in the solution. All right. So that's, a lot there. We did, I just want one thing. Yeah, I used to like Dropbox, but now it's just like a pain. But I wanted to answer Andrew's question before we do other things. But this is the output of some Python code that'll give me the A and B coefficients. All right. And again, you're going to get this. You don't have to design the filter, but you have 1, 0, and then another finite number, right? And so if this is the generic equation where you have B naught times S squared plus B1 times S plus B2, well, notice this is 0. So there's no B1. All right. So you don't need it. Right. And so then when I substitute these values into the equation, this is the equation that gets implemented. All right. So this is a second order filter. So there should be 1, 2 inverting integrators. All right. This is the A summer because it's the denominator, which has the A constants. So they're feeding back. This is negative. It's one stage of inverting integrator. So it's already negative. I keep it on the positive side. So it maintains its negativity. But here I have two stages, right? This gain times this gain, right, gives me a positive double integrator. So I need to invert that to have negative feedback. So I bring it on this side. Now, the B summer. The B summer is adding in parallel, right, the orders of S in the numerator, right? So the constants are B, and yeah, that's why I call it the B summer, although you could also say, I always draw this before that, so that would AB, right? And you can see that coming out of the output of the summer is non-inverting, keep it non-inverting. And then I have two stages, and then I keep it non-inverting. And then I balance it, right? Two inputs. Now, sure, what if I was taking the output from here, right? Well, then S2 would be 0, B1 would be 0, B naught would be 0, excuse me. So there'd be no S squared term. And B2 would be 0, so there'd be no constant term. I just have B1. And that's inverting. So in fact, I do need to add an inverting gain stage. If you bring it up over to this summer, right, I could bring it in here, right? But then I don't need this because I don't need a signal, right? And then these would be all tied to ground, right? So I'd have three of these tied to ground, but a resistor that's just tied to ground with no signal in it isn't even necessary. So there won't be any current flow, right? So if all of these are tied to ground, they're not necessary because with no current flow, there's no voltage drop. And so this would be tied to ground anyway. Well, by the time you're done deleting everything, you're left with an inverting gain stage, right? Or an inverting gain stage that adds 0 plus the signal you want. All right. So that's kind of like the mystery of, why is it there sometimes and why is it not, right? But if it was just B naught times S squared and B naught was 1, and I'm just taking the output here and there's nothing else being added or scaled, well, I don't need this at all. Same here, right? If I'm taking B2 and B2 is equal to A2, well, then it's already at the right sign. I only have one thing. I don't need this. Now, let's see if here I have 1, 0, something 0. So I have 1, 2, 3, 4, 5, right? I have 5 constants. But here, right, everything is evenly added, right? This comes out an even number, so it goes in on the non-inverting side. 2 stages, that's non-inverting. and then the fourth stage. All right. So, but now, no, still. In this case, B2, right, is not equal to A1, no, A1, A2. B2 and A2 are not the same. So there needs to be some gain, right? And so this circuit could provide it. Now, of course, that's just a non-inverting gain stage. You don't need this anymore, right? You can just calculate it as is. You don't even need that resistor. It would just come into a non-inverting gain stage. All right. That's even.
I'm still kind of unclear about adding the final summer because earlier you said whenever we're adding something in the numerator, that's when we'd incorporate this summer.
Yeah.
And then when it's a product, when it's just a standalone product, like one single product on the numerator, in theory, we shouldn't have a summer. But if you scroll up a bit, I saw an example where it was just one
right,
product on the numerator.
Because the gain needed to be changed.
Yeah, that one. Yeah.
Right. So here's the thing. This is B2, right? And B2, and so this is, no, this is
Yeah, B2 corresponds to the second op amp.
wait, something's right. So but it's also giving me A2, right? I would have calculated all of these to give me A2 to feed it back. B2 and A2 are not the same number, so I need a gain stage. Now, yeah, this looks like a non-inverting summer, right? Where I have a signal coming in, and then I kind of have a dummy on the negative side. But really, there is no other signal that I'm adding. So I can just, what I was trying to say is, I don't need this anymore, right? I just need gain. I need to make it bigger, right? Now, if I need to make it small, and now on the other hand, if I need to make it smaller, this is the only way to make it smaller with one op amp, okay?
Okay, so then if A2 and B2 were equal, then we shouldn't need this final summer.
And so in general, they're equal if there's no gain, if the gain is 1. And if you're coming out here, the high pass node or the last node is the low pass node, then you can just take it out. All right.
Okay, got it. Thank you.
Yeah, that gives people, and you can thank your teammates who came to office hours because that was like one of the number one questions. Okay, so that's why I'm prepared. Okay, but yeah, that's really. I guess what I'm saying is, there's times when you don't need that extra op amp, and so try to save it. Okay. Those were the number one questions on DF2. So I'd like to move on, move the conversation onward. No, the notch filter would be adding the high pass and the low pass nodes. Okay. So it would be B naught would be 1, and then B what's 1, 2, 3, and B4 would equal A4. That would make the notch.
So is this a high pass plus a band pass, or
No, this has only got one term in the middle, which would lead me to suspect that it's a bandpass. Or did you just say that?
I said high pass plus band pass, but I guess it's just band pass.
It's just bandpass.
Okay.
Yeah. Okay. Let me go back. So, you know, I don't want to jinx it, but I feel that people tend to do fairly well on the gain bandwidth questions. Sometimes, though, there's a little bit of confusion, or I'll say do it graphically and then you do it mathematically. If I'm asking for a particular method, it's because I'm trying to test a particular thing. So you just really kind of have to follow the instructions, if you will. But I think, but does anybody have any questions on it? Gilbert, I'm assuming you're talking about the other one. So I'll just, yeah. Where'd it go? Well, here's the thing. If you have these notes, and I have it labeled right there, out. Okay? Every single one of these has an output. Okay? So you just have to look at it. Okay? That should be straightforward. Not to give you flashbacks, that's an EE98 problem. This is not on the exam. I was fixing a typo, so don't worry, please. So for the gain bandwidth, in a way, let's just call this 0 dB. All right. And then I'm just going to draw a random thing. All right. And yeah, this is going to have, that's what that shape is. And that frequency. And all we're doing is, if we have a transfer function, and let's just call it ideal, and maybe it's a low pass, right? Maybe it's a high, right? Maybe it's a notch. Maybe it's a band pass. Maybe it's an integrator. Okay. All of these transfer functions have a magnitude. And for your circuit to work properly, the magnitude of the transfer function just has to be below that, right? And then sure, there's just constant gain, like 10, right? So graphically, right, if this is 10 dB and I draw that out, well, it's not going to work past that point. Now, in reality, it'll make it stop working before that, but that's the general place that you're at. Okay. All right. So, and if I have an integrator, right, which is a line going downwards, and yeah, what I'm drawing it where it works somewhere, right? Because if I draw this purple line over here, it doesn't work anywhere. Notice it in this case, it's intersecting at the low frequency because integrators, right, the magnitude goes to infinity at DC. So you got to keep your frequency, range above that. All right. And yeah, if this turns into a second order, oh, it'll eventually hit. But between here and here on the frequency regime, right, that's its valid reason. And either you're doing that mathematically or numerically. But the thing that kind of makes it the same, right, is that you have really we have the HS of an op amp, right, plus 1 plus HS of an op amp times G of S. But in all our examples, G of S has just been some constant because for the problems that we do that are like this, right, we're just using that voltage division on the feedback, right? Oops. Okay. But yeah, I could certainly.
So does the GS depends on if it's proportionally or derived?
In this case, it's all proportional. And I could call it K. But here's in a way, the trick. I can have a low pass filter. I can have a high pass filter. I could have something else, right? But really, it's all this, right? Or I could do this. Sorry, that's a minus sign. This is just when R2 is 0 and R1 is infinity. So beta equals 1. And here, so regardless of what's going on over here, this is if the gain bandwidth is failing at some point due to the op amp. So really, you just have to solve this part. All right. But yeah, and it's really similar. Thank you. I didn't see who said it, but right before or the last thing we did was control, right? Where H of S was out of control, and in the feedback network, we come up with a G of S that makes it in control. In this case, it was in control before, right? But we're just finding the frequency range for which it works. And yeah, we can take a system that is overdamped, and by putting it in a feedback network, can make it underdamped. So really, the controls, it's the same equation, right? And so we're really left with, right, the numerator, the original numerator, the original denominator, plus the original numerator times G of S. And the way to answer these is usually when you let open loop gain go to infinity, that's when you get your ideal function, right? So there's a lot of examples on that, but really that's kind of why maybe now you can see that it's almost the same thing. It's almost the same question, except the original thing was already in control. Right. Let's just have a bit of review here. Okay. This is an ideal op amp, so that current is 0. Now I could use KCL, but basically I can do, if I call that Vx, I can find Vx just equals the voltage division from V out, right? And now if I turn this into a signal flow diagram, there's the summer. And now I'm just going to say open loop gain as H of S. And now I'm going to bring this up on top and call it beta. Okay. And make that in. Normally they draw it the other way, but just because the feedback resistors are there, I'll draw it on top as well. All right. So then I draw my, what does V out equal? Right. V out equals in times the open loop gain, where most of the examples are H of S of the op amp, right? And then it's also minus V out times beta times open loop gain. And I'm going to switch to a darker color. You probably can't see that. All right, so now I collect the V out terms, 1 plus beta open loop gain, V in equals open loop gain, right? Solve for V out over V in, which in control systems, the new function we call Q of S instead of H of S, right? So we have open loop gain, 1 plus beta open loop gain. Now, what we're saying is when beta AV open times the open loop gain is much, much greater than 1, right? What we're really, that's another way of saying the open loop gains are going to infinity, which ultimately gives us 1 over beta, which ultimately gives us this, okay? So we just don't say open loop gain goes to infinity anymore. We're saying, in this case, beta open loop gain is much, much bigger than 1. Then we get that, right? Now, yeah, what if this were, what if this AVL was open loop gain divided by S, right? Well, I could just, wherever there's that, right? Now I can put the S, but really I get the original numerator times the original denominator, S, plus the feedback term times the original numerator. And now you could say open loop gain goes to infinity. The S drops out. But what is really that condition is when beta, the magnet, well, actually, when beta open loop gain is much, much bigger than omega. That's when open loop gain will appear to be like infinity. And then then it cancels out and that drops out and you're left with 1 over beta, right? I could have a single pole, right? And now I have to kind of put it in terms of magnitude. The magnitude of beta over L has to be much, much bigger than the magnitude of S plus A. And if it was second order, it would be S plus A times S plus B. And just say the magnitude of that. All right. So that's all. And yeah, once I get the denominator of Q of S, I can use the relations and see is it over, under, or critically damped, right? Which could be that kind of question. Okay. The next one is spring mass damper. Any questions on that? So most people draw the schematic correctly, but somehow they don't do H of S correctly. And really, you've got to have it in this form, all right? Or it's impossible to evaluate. And it doesn't have to be A1, right? That'll be R over L, right? Or it'll be 1 over RC. That's always 1 over LC. And the numerator will be something different, right? But you can't just write, oh, well, that's the voltage division. So that's going to be ZC, ZR plus ZL plus ZC. It's true, but that's not the answer, right? You've got to come up with the transfer function, all right? And yeah, there might be a bit confusion. Like when something freezes into a steel rod, right? That means it's just almost just like a wire, right? It connects these two things. It passes the information completely. It passes the velocity completely, right? And yeah, if something completely breaks away, well, then there's no connection, right? But that seemed to get people but yeah, what really happens for breakaway? Breakaway means it's no longer there, right? A spring is no longer storing energy, right, via movement, a damper is no longer passing any velocity from one side to the other. And if it's frozen, it's passing the velocity 100% from one side to the other. Okay. And then, yeah, the fact that the capacitor, one end is always tied to ground, even though it's not shown, right?
Professor,
Yeah.
can you go over the denominator when the sign change the behavior of the system?
I can't quite hear you. Can you speak up?
Yeah, the denominator. You were talking about sign the denominator last time. How when the sign change the behavior of the control.
Oh, well, that's the controls.
Yeah.
I'll do that, but I wanted to make sure we were done with this. Okay, I don't see any chats on gain bandwidth or mass spring damper. So yeah, I think you're right, Andrew. Mass spring damper can be straightforward, and most people get the picture right, but sometimes the transfer function is not right. So you kind of have to have both, and then you have to be able to know kind of what happens when when things break. Okay. So what if A1 equals 0? Okay, so let's just use the quadratic equation here, right? And I'll just say minus b plus or minus b squared minus 4ac divided by 2, right? And let's say a2 is greater than 0. All right. So if a1 is 0, right, this is 0, this is 0, and we're left with plus or minus the square root of a2j. Oop. No, and the force cancel out. Yeah. So, right, we have a pair of complex poles here at plus a2 and minus a2. All right. So that's out of control because it's an oscillator and oscillators don't settle to a value, right? So so in this case, you can use a quadratic equation, right? Where I have minus b, or I'll call it minus a1 plus or minus a1 squared minus 4 ac divided by 2, right? But this is 0, so I have I have definitely when this becomes excuse me, minus a1 plus or minus a1, I will have a root at 0 and a root at a1. But let's just look at it, right? I can do s plus a1, right? Here, that root there is negative a, or that pole there is negative a1, so it's fine. But you've got the integrator root to it, and so yeah, in that particular example, I have a root at 0 and a root here, and it's going to be like a low pass filter with an integrator. I'd have to do it, but it's just going to keep going up. Now, what is it? I'd have to do it out to see exactly how it looks, but because if I take the step function of it, right, really it's what's the inverse of whatever that is, right? And so there will be some integrator aspect to that, and so it'll keep going up. All right, but this is the one making it out of control. Right, gotta stop using that color. Now, yeah, from a shorthand point of view, I know that these signs aren't all the same, right? And so it's out of control, right? But using the quadratic equation, that's going to be a1 plus or minus a1 squared. Now this is going to be 4 positive, right? So this will never be complex, right? But the thing is we're already got a root on the right-hand side. When I add something to it, it'll be even more on the right-hand side. Possibly, I might have something where I have a root here and a root here. But this will have some kind of positive exponential increase, and so it'll be out of control, right? So now, yeah, I could have this would be out of control, and this would be out of control as well. And you can just see what happens when you use the quadratic equation. But, right, all it takes is one pole on the right-hand side, and you're going to have exponential increase. All it takes is one pole where everything is equal to 0, and you're going to have an integrator, right? All it takes is a pair of complex poles here, and you're going to have an oscillator. Now, yeah, if I had this, yep, that's not an underdamped, out of control system. It's going to have an exponential increase, sure, maybe multiplied by this. This is going to be so fast that you won't see the oscillations, and nobody really cares either. It's out of control. You need to fix it. Okay. But that's now, yeah, what could n of s could be what? S squared B1s or B2. It could be S squared plus B1s. It could be S squared plus B2. It could be B1s plus B2. I think that's it, right? And then you have to adjust things, right? Now, some things don't make sense, right? If I, like, it wouldn't be second order anymore, so I don't ask them. But if I had S squared S plus A1S, well, that becomes S, and that becomes S plus A1, and in fact, it is in control, right? So if I set the denominator in such a way that it reduces the order of the higher order terms, so no, it'll truly be a second order problem. All right. Oh, a lot of chats. Okay, so A2 for a mass spring damper for the examples I've shown, yeah, it's always 1 over LC. But, you know, what if there was, I had added an extra spring? Well, then that's a different story. Now, when a mass spring damper breaks, you can still solve for H of S. In a way, let's say this breaks. All right, so there's Vx, and then I have nothing connecting it, right? Well, there is no transfer function. H of S is just 0. That I tried to avoid those trick questions, right? Another trick question is, well, no, the other trick question I think I leave. I could have a freeze here, and then it turns into an oscillator. Or if I had the inductor freeze, then it's no longer second order. When it's not, so Justin, your question, when does a second order RLC not apply? Well, when it turns into an RC, or, yeah, it turns into an RC. Because if there's no mass, right, well, then the mass is what the velocity of the mass is what we're trying to find. And so if there is no mass, then the problem isn't worth doing, right?
So is a capacitor mass, or is that resistor?
The capacitor is always the mass, and the voltage across it is the velocity of the mass. Okay.
So you said that the only time it does not apply if it's a RC circuit, right?
Yep. Or if it just freezes totally. Here's the thing, I'm not saying there's an infinite number of possibilities, but you have to figure out each one. Okay? I can't give you a list of rules to follow. I've given you a procedure to follow. Okay? Now, listen, I ran a little bit out of time for something I had wanted to do. but you know, I think we're all feeling the effects of isolation, right? Even if we're jam-packed in the house with roommates or family, we're all feeling the effects of the isolation due to the COVID restrictions. All right. And that can really be hard to study when you're not feeling good mentally. And the things that I talked about of mindfulness and exercise, they work to an extent, but we can all feel down. Now, what I'd wanted to do to try to counteract that is move into breakout rooms where we would all kind of make at least, one contact and an appointment to study together for the midterm. One, it's really helpful to study with each other. Sure, you might be able to read answers on the Discord server or get help, but really trying to get better human contact. The reason why I didn't do that is I felt with the exam on Wednesday, people probably have their schedules set. But the first class after the exam, I know a lot of people, you might be taking the 112 exam, but I really want everybody to come so that we can take some time and make some personal connections so that you can all have a study meeting. And what I thought, I would make an assignment where you just gave me a little proof that you actually met to study. All right. And then part of that is, I talk to a lot of transfer students and they can feel that they're isolated but you're not alone. I don't know what it is, but the junior year, everybody can feel isolated. The people you went through, even if you're at San Jose State, the people you went through 98 maybe aren't taking the courses that you're taking, right? Or what if you had to repeat 110, you might feel alone, right? And so there's a lot of reasons to feel alone, even though if you're feeling alone, you're not alone. And what I want to do is try to help with that. Okay. But, I think you guys are going to do pretty well on Wednesday. Just, breathe during the exam, save the exam, and really just make sure that I can read what you scan. Just practice scanning a few things. All right. On some of the cheat sheet extra credits and things, I just couldn't see it. All right. I'll do my best to interpret it, but really, if it's neat, it's a whole lot easier to make that you have the points. Okay. Excuse me. Any questions? That I just wanted to say that before we left, but any questions on anything? All right, guys, take care. Have a good day. Oh, there's a question. Oh, the question that we don't have questions.